Okay, let's get started. Before that, hope you can see my screen and hear me clearly. If not, drop a message on chat. But welcome to the week 8 live sessions of the GPU Architectures and Programming course. And let's get started. So I hope all of you are familiar with this. So I'll skip this. Broadly, it will be a 2-hour session. We'll have a 5-minute break around the midway mark, and we'll solve questions that are similar to your assignments. And post the session, you will get access to both the slides and the recording on YouTube. Okay, with that, so this week we'll be covering week 8 topics. I know I kind of told you I'll try to cover some part of week 9, but I think this itself was a lot, so I could not add anything from week 9. In case you guys have some questions already from assignments in week 9, we can do one thing. I'll have maybe 10 minutes at the end where you can tell me questions from week 9 assignment that you're having trouble solving, and I'll see if I can find some similar problems that I can put into the slides, right? I'll do that and see if it helps you this week, and next week onwards we can see how better to do this, because accommodating 2 weeks content in one live session is a bit tricky for me also. Oh, my video is breaking. Okay, in that case, give me 1 minute. Let me just switch networks. Is it any better now? Okay, great. This is for everyone else, right? Everyone can hear me and see my video clearly. Okay. I'll take that as a yes. Please let me know if there are network issues. I always have a backup network, so I can switch networks if there are issues. Okay, so I was just saying that today, towards the end, remind me if I forget, if you have doubts in week 9 assignment. I know that submission will probably come up sometime this week before our next live session. So let me know if there are questions you're finding difficult to solve, right? 1 or 2 questions. And you can take 5-10 minutes to look through your week 9 assignment and pick out questions that you think are difficult. I'll see if I can post some similar problems into the slides by maybe tomorrow or day after, because I haven't added week 9 content into the live session itself, but maybe that's something that will help you with your assignment. We'll try that out this week and see how it goes. Okay, so today's topics are broadly around, again, continuing along kernel optimizations. We look at various fusion optimizations and various coarsening optimizations. So in terms of kernel fusion, we studied things like inner thread fusion, inner block fusion, inter-block fusion, and in terms of coarsening, we studied thread coarsening. We spoke about the coarsening factor, and then we spoke about the different types of coarsening, basically block and thread level coarsening, and we also looked at factors like stride length, right? So we'll be discussing more problems along all of these topics today, and we'll also try and have a slightly more detailed recap, because I know this is a lot to take in, right? So let's get started with the recap. And yeah, before I do that, let me go to this question that you guys had on the exam format, right? So I checked, and your official NPTEL exam will have questions very similar to the assignment questions, and all of them will be MCQs. Okay, this is the information I've received officially from the TAs. So keep solving the assignment questions, keep going through the live session material, and that should help you solve the exam questions. How many questions there will be exactly, I'm not sure about that. That was not something I could find out. So this is broadly about the exam. Any other questions on logistics you guys have before we move on to this week's content? And today there will also not be a discussion forum section in this session, because I think all 2 or 3 of the questions that were asked were about OpenCL, which is technically next week's content, right? So we have covered everything up to week 8 in the discussion forum. So we'll basically be going ahead with the recap of what was done in the session, and then we'll move ahead to problem solving. Okay, if there are no other questions, let's move to the recap. Oops. Okay, so coming to before we start with kernel fusion, right? To motivate it, or to give an example that you guys can kind of relate to, we start off with this idea of loop fusion, which is again a common compiler optimization that is done in programming, and it's very similar to the kernel fusion idea, right? Basically you want to improve performance, and so you keep the memory hierarchy diagram that we had discussed, I think, in the very first week, right, where we did our computer architecture overview. So we said there is registers, and then there is cache, and then there is main memory, and so on. So the more and more traffic you send off chip, the more your performance drops. So the more you can reduce this off chip traffic, you get better performance, right? So that's the whole motivation, and what we do is very simple. We fuse iterations of different loops because those reference the same data, right? And the benefit that you gain from doing this is multiple. One is the cache benefits, right? So if you have I think we looked at this toy example. So before the fusion you have 2 loops, both one is iterating over a of I plus, one of them does a of I plus 3, the other does b of I plus 4. And now after you fuse it, what you do is you simply have the same loop, and then you do both of these inside, right? So what's the advantage of doing this? So one thing is your loop overheads, this checking, condition checking, this increment, all of that now becomes just once rather than twice, right? And this is a benefit that you gain. Comparing this to your CUDA kernels, the kernel launch can be thought of as something like this. So remember again, even whenever we write the host code or the driver code, right, we actually do a kernel launch. So you remember, we call a kernel and then we specify the parameters of the kernel, right? But the CPU is actually responsible for doing this launch onto the GPU, right? That's why it's written as part of the host code. So this takes some amount of time to actually launch this kernel with all of these parameters, to copy some data onto the GPU. All of that takes time, right? And that is an overhead. So if I launch this kernel and I have, let's say, one statement, and then again I launch another kernel and I have one more statement, then what happens? This kernel launch overhead that I have to execute this one statement is a lot. Now instead, if I can have just one kernel launch statement and do both of these things, then I'm saving on that overhead. So it's that same idea that happens in loop fusion, right? That's what we use. Then additionally, you might have things like reduction in cache miss. For instance, if both your loops are accessing the same a of I, maybe one of them does a of I plus 2, the other does a of I plus 3. So you save. Now what happens if I finish the entire loop 1 and then go to loop 2, right? Let's say this a of I is very big and it doesn't fit into the cache. So by the time I'm accessing this array sequentially, right? So I access it, and by the time I come to the end of the array, all the things at the beginning of the array are no longer in the cache, because the cache is again something that's of limited size. so it cannot hold the entire array, right? So going by the LRU policy of the cache, the least recently used, it will keep flushing whatever was seen very early. So it will keep only the last few. But now you come to the second loop and you're again going to access these elements at the beginning of the array, none of which are in the cache, right? So it will all cause cache misses, and again you will have to pay that cost of bringing it into the cache, the memory cost, right? So that can be avoided if you club multiple loops into one, because now you bring this into the cache and then you perform two computations on it. So the cost of bringing it into the cache is amortized across both of these operations, or how many ever operations you are fusing. So that's always a benefit whenever you fuse, right, the cache parts of it. So that's the idea behind loop fusion, and also similarly kernel fusion. And before we get into the details of kernel fusion, right, this is again, whenever you learn concepts in this course, remember that they are not very theoretical. You actually see many of these things happening in practice. So think about whether you've seen something like this. So for instance, I have seen tools that do kernel fusion. For instance, you guys might have heard of deep neural networks, or DNNs, right? A lot of AI workloads use deep neural networks in them, and so typically, if I were to tell you about a deep neural network, there are two processes that happen for people who don't know, right? One is the training of the DNN, and then the inference or the testing of the DNN. So in this and this inference typically is very latency sensitive, as in the user cares about when they submit something for you to do an inference and when they get back the results, because typically it is used in very real time use cases. For instance, let's say there is an autonomous vehicle and you want to do an object detection. So the camera on the autonomous vehicle gives you these frames live, and maybe you run some object detection model like YOLO, right, to get the objects in the frame. Typically, you would have a latency of 100 or 200 milliseconds to do this inference, right? So inference is latency sensitive that way. So then how much time it takes to do this inference is very critical. So let's say my deep neural network, let's talk about a toy DNN which has 3 layers, right? Maybe real world DNNs actually have a lot more than this, but for now let's just say they have 3 layers. And let's also say for simplicity that each of these layers maps to one kernel. So now again the same thing happens here. So you need to launch 3 kernels for these 3 layers, and that might take you X amount of time. Now if I wanted to reduce this X, obviously because I can get better performance, if I finish this workload faster, I'll be able to handle more and more frames, right? So if I want to do that, one optimization that is typically done in industry standard tools is kernel fusion. So they might try to fuse these 3 kernels into 2 kernels, or maybe even 1 kernel. And why do they do that? Again, like we discussed, we get all of these benefits by doing that, right? And ultimately your execution time of this inference model goes down because of doing kernel fusion. So this is actually done in today's tools. For instance, one tool that does this is called TensorRT, which is provided by NVIDIA for accelerating inference workloads on their GPUs. So I just want to talk about this so that you guys appreciate this in real world scenarios. It's not something very abstract that we are learning about. It is something that is done by state-of-the-art tools today, and it does give you better performance. You will notice that TensorRT tells you gives you performance numbers. They'll say if you run this inference without TensorRT using standard deep learning frameworks like PyTorch or TensorFlow, it takes you X seconds, and if you run it using TensorRT, it takes you Y seconds, and this Y will usually typically be much less than X. And one of the optimizations they do to achieve this is kernel fusion. So this is just some meta information on that. Okay, coming back to kernel fusion, it's an optimization technique, as we discussed, it decreases execution time. It could also decrease power consumption. That's very interesting, and again depending on where you use these things, right? For instance, you might be using it in a GPU which is used on an edge device, which means that this GPU might actually be mobile. For instance, it might be on a drone, right, where power consumption becomes very critical because you have a limited power bank or some kind of a battery powering the device, right? So this is an optimization technique that helps you reduce both execution time and power. And kernel fusion basically rearranges and kind of schedules the kernels from the host side. Basically, once you launch them to the GPU, you have no control over how they are scheduled. That's done by the scheduler. So what you need to do to change something about how the kernels are executed is to rearrange or fuse the kernels from the host side itself. Basically, when I launch, I make sure that I'm doing these optimizations, because after the point of launching, the CPU or the host side has no control over the execution, right? So again, kernels using the same or different data arrays can be replaced with a single kernel call. The new kernel aggregates the code segments of the separate kernels. So broadly, this is the idea of kernel fusion. Again, why does it increase efficiency? So you have data reuse using on-chip memory that improves performance. Again, you reduce off-chip memory traffic. You reduce global memory data transfers. You reduce kernel launch overhead, and you utilize maximum threads in the GPU. I think all of these are clear. Okay, so coming to some of the limitations. So why would kernel fusion not always result in performance improvement? So all of these optimizations, right, you have to ask yourself this question: when will it improve performance? When will it not improve performance? And some of these things, like I always say, it's a combination of your software problem and the hardware that you have. So anytime you say that something will be better because of XYZ, you should think of both sides of the coin, right? From a software perspective, for instance, here we only spoke about the program, the code, right? So from a software perspective, fusion made sense, but from a hardware perspective, does it make sense? So that's one of the limitations. So the architectural resources, for instance, your on-chip memory or your registers, are limited. So if you fuse these kernels and make them consume more on-chip memory or more registers, that might cause certain other side effects as to how many threads you can possibly launch in parallel, right? So that might again cause some performance degradation, right? So you might not always get the theoretical performance improvement that you're expecting. The other thing is the overhead in identifying fusible kernels. Now imagine that you are doing this kind of compilation, right? So typically, again, going back to the deep neural networks example, I'm sure some of you have at least tried out basic models, right? So you write this in PyTorch, and thereafter a compiler comes into play, and then it launches these kernels. So now if you were to do optimizations like this, they would have to be done by that underlying framework or runtime, right? And so that means that it first has to identify which of these are fusible and which of these would give you performance benefits. So that itself would take some time or some overhead, right? So many of these optimizations mean that you have to spend some time first figuring out where to optimize or what to do, right? Again, some of that might be tolerable, like you can justify it, maybe saying I do this at compile time, not at runtime, and maybe once I do it, again going back to the deep neural network I had, if I tell you that I'm going to be using this network, once when you compile this network, maybe you need to identify these fusible kernels, but thereafter I'm going to use the same DNN for hundreds of frames coming in through the camera. So maybe that overhead is justifiable, right? These are things that you need to think about whenever you propose some kind of an optimization. Similarly, you have an overhead in searching for the optimal rearrangement of fusible kernels. So one trivial example that we saw was K1 and K2 are kind of independent kernels. Now you can execute them as K1 followed by K2 or K2 followed by K1, right? Now does this have a difference in performance? This is a very simple example I'm giving you, but basically this is the idea, right? How do you rearrange these properly, optimally, so that you can reduce execution time? So these are some of the limitations or some of the overheads that you have when you bring in things like kernel fusion. So a quick example here, I think this was given in class also. So you have K1, K2 and K3 here, and the important distinction to note is that K1 and K2 are independent. You can run them at the same time, and then K3 depends on the outputs of K1 and K2. And instead here you have a fused kernel, that a big thing that takes, that basically does whatever K1, K2 and K3 were together doing, right? And you would notice here that this global memory is avoided. You only have global memory at the boundaries of this kernel. Inside it there is no global memory. So that's again one of the advantages of kernel fusion. Okay, so before we go to the types of kernel fusion, is this idea clear? I spent a good amount of time on the recap because I think as we move ahead, the topics are getting a little bit advanced, and you guys said last time that you're having trouble understanding some of those things. So is this whole idea clear, or do you have some doubts about it? Okay, I'll take that to assume there are no doubts. So overall, how is the course going? Is week 8 okay? Was everything understandable, or do you guys feel like it's too complicated, you're not able to solve the assignments? Okay, week 8 assignment questions are tough. Yeah, I think from last week itself, that's what happens with a course like this, right? Some of the initial weeks contents are typically lighter, and also I think you had lesser videos. You had 3 to 4 videos per week, and from last week I noticed that there are at least 6 to 8 or 9 videos per week, right? So you have a lot of content to understand, and also solving the assignments is not so easy as in the early weeks. So yeah, I understand where you're coming from. We'll try to work on a good amount of questions today. Okay, let's keep moving forward then. So there are 3 types of kernel fusion: inner thread fusion, inner block fusion, inter-block fusion. So let's look a little bit at each of these. I won't go into too much detail because again it was covered. I think we spent almost one lecture on each of these things. But if you have doubts on any one particular type of concept, please ask, and I'll cover that in detail maybe in the next session. It's very important to understand these fully and properly, right? Because solving assignment questions is not possible without that. Even when you understand it fully, you will still need to think a lot about the assignment questions. So if you're not clear about the concept itself, then it gets harder to solve the assignment questions. So if there are any concepts that are not clear, please highlight them. We'll spend enough time trying to understand them. Okay. So starting with the simplest one, which is inner thread fusion, right? So this is what it looks like. So you have your kernel 1 and kernel 2, and there are some amount of threads in kernel 1 and kernel 2. Now what you do is you increase the work per thread, right? So every thread is now going to do some amount of work for kernel 1 and some amount of work for kernel 2. This is how it's going to be. So basically it combines the computation of two kernels into a single thread. Now why is this beneficial? Again, we spoke about it. There is one kernel launch and then you do some per thread activity, right? So the more per thread activity you can do for a single kernel launch, you gain something in performance. Basically think about it as maybe, let's say something simple like starting up your laptop takes 5 minutes. You have a very old laptop and it's very slow, and let's say you start it up and it takes 5 minutes to fully boot to the OS, and then you do 1 minute of work and then shut it down, right? Now what's the problem? It's very obvious. Out of 6 minutes that you spend, 5 minutes is spent doing nothing. It's just an overhead, right? So how do you optimize this? Each time you start your laptop, you try and do more work before you shut it down, right? It's very simple. It's similar to that. So we try to do more per thread. So here you combine the computations of both those kernels into a single thread. Now this is suitable when the data size space is the same, right? If you have the same number of threads, so how do you get the dimensions of the threads and the blocks in the kernel? So this STH represents number of threads, SBK represents number of blocks. So you simply take the maximum of both for both the threads and the blocks, right? But in case this does not have an equal number of threads or threads per block, right? If the two kernels that are involved, K1 and K2, don't have the same number of threads per block, then that might be a little inefficient, right? Why is that? Because now one thread might be doing both K1 and K2's work, whereas another thread might be doing only K1's work, right? So there's kind of not very balanced work across threads, and it will remain idle. You'll have lots of problems because of this imbalanced workload, right? So that's a condition under which this is not suitable. So here if you see, right, it's drawn as if both of these are equal. So what if it's like this, right? So then a bunch of these threads will be doing only one kernel's work. That's what we are trying to say. So it's suitable when it's very suitable when it's like this. It's equal number of threads. Okay, so looking at the example here, so you have K1 and K2 and this is your fused kernel. Here everything is the same, right? Both of them have 2 threads per block and the fused kernel also has 2 threads per block. So there's no issue. So we won't go into the detailed examples. We'll move to the next question, next topic. So the next topic is inner block fusion. So now it looks slightly different, right? Keep these pictures in mind for each of them, right? That will help you remember it better. So inner block fusion looks something like this. This is kernel 1 and this is kernel 2. So depending on the thread ID, some of the threads will do kernel 1 and some of the threads will do kernel 2, right? Now think about this. So you had this inner thread fusion where you do something like this, right? But going back to this simple example, K1 and K2 were not at all dependent, right? They are two independent kernels. So do you have to wait for a thread to finish kernel 1's activity to then go to kernel 2? No, you don't really have to, right? So another way of parallelizing it could be to have different threads doing kernel 1's work and different threads doing kernel 2's work, because they're not really dependent, right? So you could do something like this. Depending on the thread ID, you could do the kernel 1's work and you could do the kernel 2's work. So here the idea is to distribute the computation of two different kernels among threads in a single block, and this can be done for independent kernels, right? That's the key thing to remember. You can't do this for something like K1 and K3, right? Because if I ask 4 threads to do this and 4 threads to do this, these 4 threads have to actually depend on the output of this, right? So they won't be able to do that. They have to get this output. So this is only a good idea for independent kernels. And again, using the same notation of STH and SBK. Now there is a slight difference. For the fused kernel, your SBK, the blocks in that fused kernel, is the same. It is the maximum of the two. But the threads now is the sum of the two. Why is this? Look at this picture, right? You need some amount of threads to do kernel 1's work and some amount of threads to do kernel 2's work. Now let's say this had 5 and this had 5 originally. Now if I just took max of these two, which is 5, I'm not going to get the desired parallelism, right? Because I have fewer threads than what was originally intended for this kernel. So instead I will do 5 plus 5, which is 10, and I'll make sure that both the kernels have the same number of threads as originally intended, which is 5 and 5, right? So that's why it changes to sum of STH1 and STH2. And when does this become a problem? This fused kernel STH exceeds the upper bound of threads per block. So again, remember that there are all these hardware imposed limits. So you have to make sure that both of these are within that. And again, if you have kernels with synchronization statements, this might be unsuitable. So this was inner block fusion, and again this pictorial representation gives you a good idea, right? So this is the blue and the yellow, and you can see now that when they are fused, this is your block, and some threads in the block do the work of the first kernel and some threads do the work of the second kernel, and notice that they are independent kernels, so you can actually do this. So that was inner block fusion. Yeah, and limitations, as we already said, this upper bound is architecture dependent and it should not exceed this upper bound. CUDA doesn't support synchronization for partial threads in a block. So if you have something like a sync statement like we saw in the reduction kernel, then that is also not applicable because you can't do a sync on a certain number of threads in a block. CUDA doesn't support that, right? So things like those would again be a bottleneck to doing inner block fusion. You should not have a sync statement within a kernel. Okay, so before we go to inter-block fusion, any doubts in these two? I'll just wait 30 seconds. I know we've covered a lot. Might have been clear to you when you watched the lecture, but in case it's not, take a few seconds to look through this. Any doubts so far? Okay, if not, let's keep moving ahead. So next there is inter-block fusion. So notice that this blue thing might look very similar at first glance, right? But here what are we talking about? We're talking about threads in the same block. That's why it's inner block fusion. Here we are talking about a grid where these are in two different blocks, and we are doing this now. For kernel 1 is being done by some threads here in a particular block, and kernel 2 is being handled by threads in a different block, right? This is inter-block fusion. So here the idea is to distribute computation of two kernels among different blocks. Again, we want to do this for kernels with similar computation time. So remember previously we were talking about having an equal number of where was that? Probably in inner thread fusion. Yeah, here, right? So if we have kernels with a different number of threads per block, we might end up having different work across threads. There is not balanced work across threads, right? Similarly here, we want balanced work across blocks too. So that's why we want independent kernels with similar computation time. We don't want one block taking too little time, one block taking too much time, right? And again we'll carry on with the same STH and SPK notation. So here we do the reverse. The number of threads is the maximum of the two, but the number of blocks is the sum of the two. Because remember now, if you had say 4 blocks for kernel 1 and 4 blocks for kernel 2, if I did max of kernel 1 plus kernel 2, again I am reducing the parallelism in the implementation, right? Which I don't want to do. I don't want to change any of that. I want each of these kernels to execute the same way as they were originally intended. So what I do is I do 4 plus 4, 8 blocks. And threads, as far as threads goes, I don't change anything. I keep it as max of STH1, STH2. Again, this won't be suitable if the workload of blocks differs a lot, because you don't want that imbalance across blocks in this case. So coming to a quick example, this is what it looks like. So here notice that they have different number of blocks, right? And this is what the fused one looks like. So yeah, so that was all 3 types of fusion. So moving forward to a different idea. So we are done with fusion. Now we are talking about something else called coarsening, right? What is coarsening? So as part of parallel execution, sometimes what happens is we do some redundant calculations or memory accesses. So to avoid this, we merge multiple threads into one. That is called thread coarsening. Why do we do this? Because we can reuse the results that we get. We can avoid redundant work. And this is similar to the loop unrolling idea that we had seen earlier. But here it happens across parallel threads rather than across loop iterations. So yeah, again thread coarsening has some beneficial effects, and what are they, or why do those happen, right? So coarsening requires lesser number of threads to be launched, and this was the interesting part, I think. Increased number of instructions increases scope for exploiting hardware level parallelism. Not this part. Where was okay, so I think that comes later on, where remember that you might not always see a benefit to thread coarsening. So you might, again, because of these hardware effects, right? If you coarsen a thread, basically you combine the multiple threads into one. Because of that, one thread itself, let's say one thread was consuming 4 registers, and now you combine 2 or 4 threads into one. Now it takes 16 registers, right? Now because of this, it might limit how many threads you can run in parallel. Why does it do that? Because you have a fixed number of registers, and you cannot exceed that limit. That's a hardware limit, right? And because of this, you might have what is called reduced occupancy. I think this part is not put in the recap, but it is something important that you need to remember. Occupancy is basically how many parallel threads can your hardware support per SM, and how many do you actually have. And how many you actually have running might be limited by this registers and memory also, right? So that's one place where thread coarsening might not really help you. So that's something to keep in mind. And I think I've not gone to any of the coarsening details. So this is all the recap we have for this week's content, but it was a lot. I think I looked through the content, so take a minute to see if all the ideas are clear for you, and put any topics that you want in more detail, in covered in more detail in the chat, right? We'll spend 5-10 minutes in the next live session going through them. Any doubts? Any doubts in week 8 topics? For people who just joined, we've been going through week 8 contents today. So we just finished the recap and we'll be moving to the assignment questions shortly. But take a few seconds to let me know if there are some topics in week 8 that are not clear, right? So the lectures covered a bunch of topics along kernel fusion, thread and block coarsening. So if there's something you don't understand from this list of topics, please put that on chat. We'll go through that in detail in the next session. I'll wait a few more seconds since there are a few people who just joined. Okay, if there are no doubts, we'll move ahead to the problems. Yeah, like I said earlier, there's nothing from the discussion forum today. I think there was nothing on this week's content. So we'll skip that and move ahead to problem solving. So these are again the long questions, right, that are common to 2-3. The data is common to 2-3 questions. So we'll go through them in detail and then look at the questions. So consider two independent CUDA kernels as given below to be run on a target GPU with 32 SMs and each SM supporting a maximum of 2048 active threads per SM. Assume there are as many SFUs as the number of active threads per SM. The calling kerning parameters are, so there are two kernels and it's 1024 comma 1024 for both of them. Now we look at the kernel descriptions of both those kernels. So here's kernel 1. So you calculate LTID as threadidx.x. If it's less than 512, you do in1 plus in2. If not, you do sine of in1 of GTID plus cos right? These are the operations that are done by kernel 1. Moving forward, kernel 2 similarly calculates LTID, does the same check for less than 512. It does a sine plus cos here, and it does a sum here, right? So these are your two kernels. This does a sum here and a sine plus cos here. This does a sine plus cos here and a sum here. Now assume that each float type sine cos operations takes 20 cycles and each float addition operation takes 4 cycles. Ignore any penalties due to memory access and data transfer. So this is what you're told. The sine cos operations will take 20 cycles and additions will take 4 cycles. Ignore everything else. Calculate the total number of cycles it will take to compute the inner thread fused version of the two kernels. Consider execution time only due to these factors. What is the total number of cycles? That's what is asked. So here are your options. Maybe quickly note down these three options and we'll go back to the kernel definitions. I'm sure it's a long question, so I'm sure you'll need some details from there. I'll just pause here and then go back to. So here are your four options. None of the above: 1024, 1536, 3072. And you're asked for inner thread fusion. Now going back, here is the architectural details, right? 32 SMs, 2048 active threads per SM, and these are your launch parameters, and this is your kernel 1. I'll wait here for maybe 15-20 seconds and go to the next kernel and take 3 to 4 minutes to solve this, and then we'll discuss the answer together. Okay, let's move on to kernel 2 and I'll pause here. If you need the options again, just post a message on chat. Try and work this out on your own. Take the time and then work it out and let me know the answer. Any answers so far? Here are the options again. So we went through what is inner thread fusion, right? So you have these two kernels. Now you will do inner thread fusion on them. Think about what happens to the number of blocks, the number of threads for the fused kernel, and then think about how many cycles it will take for each of these operations, and then think about the fused version. I'll give you one more minute and then we'll discuss the answer. Are you stuck somewhere? Are you having trouble calculating something? Do you need more time? Okay, we can go to the explanation if there are no answers. So the answer is B1536, right? Let's think about why that is. So first, let's talk about the number of cycles. So you're going to fuse these two kernels, right? So let's talk about the unfused versions first. So we have one addition operation here. So we are told this takes 4 cycles. And we have one sine, one cos and one addition here. So the sine takes 20 cycles, the cos takes 20 cycles, and then the addition takes 4, right? So this is 24 plus 20, 44. So this kernel takes 4 plus 44 cycles. This kernel is basically the same set of operations but reversed. So again this takes 4 cycles, this takes 4, 20, 20, so 44, right? So both of them take 44 plus 4, 48 operations. Now if I do inner thread fusion, again let's go back to what is inner thread fusion, right? So you have one thread doing the work of both kernel 1 and kernel 2, meaning one thread will do this 44 plus 4 cycles for the kernel 1 and then the opposite, right? 4 plus 44. So let's go back to this question. Yeah, so for the total number of cycles that you will have in the fused kernel is 4 plus 44 plus 4 plus 44, which is 96. But now you're asked the execution time not just for a block but for the entire kernel, right? And remember the kernel has 1024 comma 1024 as its thread, a number of threads and number of blocks, and remember that the fused kernel in the inner thread case will have the maximum of the two as its dimensions. So that kernel will also have the same launch parameters 1024 comma 1024, right? So now think about how many times this needs to be executed. So how many number of batches that you have. Basically that will be your number of threads, which is 1024 cross 1024, total number of threads, but this will all happen in parallel, right? Remember, your GPU has multiple of these SMs, and then within each SM also you have multiple threads running, right? So that is your denominator. So how do you get that? Here you have 32 SMs, and each SM can support 2048 active threads, right? So you take your total number of threads and you divide it by 2048 into 32, right? That's your hardware imposed limit. So you get the number of batches, that the number of times this has to happen, as 16, right, for this fused kernel. So for one such batch it takes 96 cycles. So for 16 of these batches it takes 16 into 96, 1536, right? And that's how you get your option B. I'll pause here for 30 seconds. I know there's a lot to this solution, so think about it, see if you understand it well. If not, ask me your doubts and then we'll take a break. Any doubts? Okay, if it is a little complicated, you can go through this solution later as well after the session ends. But let me know if you don't understand something or something is very confusing, right? It's important that you understand how this is and why this is. So we are almost at 8:04 now. So let's take the 5-minute break and we'll come back at 8:09, right? 5 minutes from now. I'll keep the call running, but we'll resume at 8:09. Take the break and then we can continue. Okay, let's continue. Okay, I see a question. Can you explain how 32 is there? Sure. Okay, so this is in this number of batches computation, right? So first of all, 32 comes from this number of SMs present on the GPU, 32, right? So re-explaining this calculation, we are trying to find out how many such batches there will be. So the total number of threads is 1024 into 1024 divided by total number of threads per SM 2048, which is also a hardware limit, and the total number of SMs, which is 32, right? So you get this to be 16. You can even do this calculation another way, right? Let's try that out. So totally we have 1024 blocks, right? And we have 32 SMs. So at a time, how many blocks can be executed? So each SM has a thread limit of 2048, and we know that here one block has 1024 threads. So at a time we can execute 2 blocks on one SM, right? So this is 2 blocks per SM, and we have 32 of these SMs. So at a time we can execute 64 blocks on the whole GPU parallelly. So how many batches do you need for 1024? This becomes 1024 divided by 64. This is 2 power 10, this is 2 power 6, 2 power 10 by 2 power 6 is 2 power 4, which comes out to be 16. We're basically trying to find out how many times do you need to do this execution, right? Given that you have 1024 blocks, and the 32 comes from the number of SMs, the 2048 comes from the number of threads. Now is this clear? Take a few seconds to understand it. Okay, it's clear. Any other doubts in this question? Okay, if not, in the interest of time, we will move ahead. So question 2 uses the same data, right? So remember these things, 32 SMs, 2048 threads per SM, the same two kernels with launch parameters as 1024, 1024. Now make this assumption that blocks are scheduled in a round robin fashion to the underlying hardware. Block 0 to SM0, block 1 to SM1. Calculate the total number of cycles, again only due to these three operations, for the inter-block fused version of the two kernels. And again you have three options. Think about it. Try to solve this one. Now that you've solved the previous one, this should be relatively easier. Only thing is it used inter-block instead of the other one which used inner thread. Right? So think about it. Take 3 minutes to do this. Any answers so far? We'll wait 30 more seconds and then look at the answer. Okay, if not, let's go ahead. So it is again 1536, right? So let's talk about how this is. So again, the total number of cycles is 44 plus 1 for kernel 1 and 44 plus 1 for kernel 2. This remains unchanged. Now remember that each of these kernels is launched with 1024, 1024, right? So what will happen now is, let's go back to inter block fusion once. So remember that the number of threads is the max and the number of blocks is the sum of the two, right? And this is what the fusion diagram looks like. So if this has this many blocks and the yellow one has this much, when it's fused it looks like this, right? These blocks handle the blue kernel and then these handle the yellow one in the fused one, right? So now going back to our question 2. So if I do an inter block fused version, the first 1024 blocks will execute operations for kernel 1 and the next 1024 blocks of the fused kernel will execute operations for kernel 1, because remember now the number of blocks that you have will be 1024 plus 1024, which is 2048. Now out of these first 1024 blocks which are going to execute kernel 1, that will take how many batches, right? Just similar to the previous question, you need to find this number of batches again. So this remains the same because number of blocks is the same, number of threads is the same, the hardware number of SMs and number of threads per SM are the same. So you get the same 16 batches, right, for kernel 1. So now for these 16 batches, what is the time in cycles? So it takes 44 plus 48 plus 4, which is 48 cycles for one batch. So for 16 batches, it takes 16 into 48, which is 768 cycles. Now remember that this is only for kernel 1. So similarly, if you do for kernel 2, that is the next 1024 blocks, you'll again get the same 16 batches because again the launch parameters are the same, the hardware config is the same. So you get the same 16 and the number of cycles is also the same 48. It's just 4 plus 44, 44 plus 4, right? It's the same. So you again get 768. So the 768 plus 768 comes out to be 1536, right? So the answer is option A. So if you look at the previous one, it was just 16 into 96, right? In a way, you can think of this this complicated fusion as 16 into 96. You're just splitting it into 16 into 48 plus 48, right? So the cycles actually remains unchanged. It still remains the same. That's one high level view of thinking about it. But again, remember that we are making a lot of assumptions here, right? We are taking into account only the cycles for sine, cos and add. There are a lot of other factors that come into play, as you've realized with the case studies and the performance info during the course, right? But given that we consider only these three, the interblock fused version and the inner thread version take the same number of cycles, which is 1536. Again, I'll pause here for 30 seconds. Think about the solution. See if you have some doubts. Ask me. If you feel these are still difficult, can we conclude that interblock fusion is ineffective for this case because cycles are same even for the unfused case? Theoretically, you can draw such conclusions, but in practice, a lot of other things come into play. So, yeah, from this information given for the question, conclude you can conclude that. Let me think about it and see if there's something else to consider. Yeah, I would say broadly that you can make the statement from the data given in this question. But remember, right, if we go back to, again, I'll say the same thing that I said. A lot of the benefits of fusion and more generally the loop fusion. Let's take the simple example, right? If I asked you to count just the cycles here, it would be, let's say this takes one cycle, this takes one cycle, you would still get the same two cycles here, but this is definitely going to be faster because you will end up with certain other benefits that are not evident from the program itself. One thing is, for instance, let's say both of them were accessing A, you would get cache benefits. Similarly here, the loop overhead in this case is visible from the program itself, right? But remember, when we are talking about these kernel fusions, we are only accounting for the cycles from the arithmetic operations. We are not actually talking about the overheads of launching these kernels, right? So if you took into account some of those other numbers, you would get very different results, and that's what the practical examples in the course highlight, right? You saw some graphs showing performance, and you saw, for thread coarsening for instance, you saw that a certain coarsening factor is effective. So in reality, this might not be the case, but for this toy example, from the data that you are given, it is reasonable to make the conclusion that you have made. Great. Okay, let's move ahead. This is a very simple question considering question 1 and question 2. So now consider these two kernels with modified launch parameters 1024, 512, 512, 1024. If I do an inner thread fused version of these two, what would be the launch parameters? Think about this. It shouldn't take more than a minute. We've already discussed this in the recap and in both the questions. So just think about it. Okay, we have one answer saying C. Great. Anyone else? Okay, C. Great. Anyone who thinks something else is the answer? Okay, I think this is a simple one, so we'll go ahead and look at the answer. It is C1024, 1024. For people who don't understand why, let's go back to the inner thread fusion. So this is how inner thread fusion looks, right? So you have your kernel 1 and kernel 2, and the same number of threads work across both of them, right? Like one thread will be doing activity of kernel 1 and also kernel 2. So remember that we said we're going to do max of both, we are not going to change. So both of them have equal, for instance in this example, right, both of them seem to have, let's say, 8 threads, right? So then in that case we do max of 8 comma 8, which is still 8. Similarly for the blocks we do a max, and if that's also the same, it remains the same. Let's say it's not the same, let's say it's 8 like here, right? Let's say this is 4 and this is 8. Now we don't want to decrease the parallelism of this kernel by forcing it to do 4, right? So we'll retain the 8. We know that there is going to be this caveat of unbalanced workload across threads, but this is the best we can do, right? So that's why we do max in case of inner thread fusion. Going back to our question which asked about inner thread fusion, you're going to do max along both of these dimensions. So 1024 comma 512 is 1024, 512 comma 1024 is 1024. So this, your fused kernel will be launched with these parameters. Any doubts in this? This is an easy one, so try to, if those two questions were very tough, at least this should be easier. But if you still have questions, don't hesitate to ask. Okay, if not, let's move ahead. Okay, another similar question. So kernel 1 1024 comma 1024, kernel 2 512 comma 1024. What will be the kernel launch parameters for an inner block fused versions of the two? 512 comma 1024, 1024 comma 1024, 1024 comma 2048. Think about this. Again, you don't need to mug up these things, right? Max of, sum of. Think about it logically and try to arrive at the answer. That will always work even if you forget. So try to reason it out. Take a minute. Any answers? Okay, we have one answer C. Great. Anyone else? Anyone else? Okay, maybe let's try to make this easier so that next time you guys don't forget this. So the answer is C, as someone had correctly said, 1024 comma 2048, right? So like I said, let's not try to mug up these formulae. Let's try to reason it out, right? So we were talking about inner block fusion, right? All you need to remember is this diagram. With this you can kind of reason it out. So here you have some threads inner block doing the work of kernel 1 and some threads doing the work of kernel 2. Now think about this scenario. What do I need to do with the number of threads? Can I just take max of kernel 1 and 2? Then I'm changing something about the way the data space and the parallelism of these kernels is defined. I don't want to do that. I want to have the same number of threads as before for kernel 1 and the same number for kernel 2. So I simply am going to add the number of threads, right? But do I have to change anything about the blocks? No, I'm not at all touching something across blocks. So the blocks will remain the same, right? And that would be the max of the two, just like we did in the inner thread fusion. So the threads will be the sum of the two and the blocks will be the max of the two. You don't need to remember this, reason it out. That's always better in case you forget it, right? So now going back to question 4, right? We were in question 4, yes. So yeah, so now your threads becomes 1024 plus 1024, 2048, and your blocks becomes max of 1024 comma 512, which is 1024, and that's your option C. Hope this is easier to understand and remember now. In this whole portion, I think these are your easy questions, right? With the whole thread coarsening and the fusion, this launch parameter part is perhaps the easiest one. So make sure you get that right. Any doubts here? That's why we kind of went through these in detail at the beginning, so that at least these easy questions are, a little more clear to you. Okay, I'm assuming that's clear. We'll move ahead. Very similar question. Kernel 1 512 comma 512, kernel 2 512 comma 1024. What will be the launch parameters for an inter-block fused version of the kernels 1 and 2? 512 1024 1024 512 1024 1024 1024 2048. Again, take a minute, reason it out from first principles. Think about what you remember about inter-block fusion and think about what you would do to the number of threads and number of blocks for this new fused kernel. Right, the common data questions are definitely tricky, and they require you to pay attention to a lot of parameters, right? There's a lot of information in that question before you can answer. So it takes time and effort. So these questions on the contrary are easier to answer. So if you're looking for strategies to manage your time, think about that, right? Solve questions that are easy first and then move to the hard ones, or however you want to do it. With a timed exam like this one and probably GATE, right, all of those become important. It's all MCQ, so you need to think about what you want to solve first and what you want to solve later. Since your exam will be very similar to the assignment questions, right? Notice how you're spending the time on the assignment questions also. Which questions take a lot of time for you? Where do you make mistakes? Things like what you just pointed out, right? You have some common data and you make a mistake in the first one, it propagates to all of them. So those are things to strategize better for the final exam. Okay, coming back to this one, think about this. I'll wait a minute more and then we'll discuss the answer. Okay, we have one answer C. We'll wait a little more to see if any others have answers for this. other answers? Okay, I think this was an easy one. So let's go forward and look at it. So it is C 1024, 1024. Again, like we did for all these questions, let's go back and look at the inter-block example, right? So this is what an inter-block fusion looks like. Remember that this is a grid and this is a block boundary, right? So we're talking across blocks here. So again, think about this now. Do you need to change the number of threads? Do you need to sum it up? No, you don't need to. So it will remain at max of thread 1 comma thread 2. Whereas the blocks, now remember that some of the blocks are doing only the work of kernel 1 and some of them are doing only the work of kernel 2, right? So then you need to increase the number of blocks to account for that. So think about along which dimension you are splitting the work, and therefore what do you need to increase, right? So in the previous example, it was along the dimension of threads. Some threads were doing kernel 1's work and some threads were doing kernel 2's work. Here it is some blocks. It's the granularity of blocks, as the name says, right? Inter block. So then you need to sum up the number of blocks. That's the answer to this. So now going back to our question 5, right? Yeah, so summing up the number of blocks gives you 1024 and taking max on the number of threads gives you 1024. That's why it's option C. Hope this is clear. So to answer these questions, you just need to understand clearly what are the three different types of fusion. How do they parallelize the computation, right? Once you understand that, this will become easier to solve. So like think of a contrast between the three. Maybe draw out all three on the same page and write down this thing. Write it down as in, don't copy it from here, derive it on your own. Draw that diagram and think about what it needs to be, the way we just did, right? And do that. Once you do that, I think all of this category of questions should be very easy to solve. Any doubts here before we move on? Great. Let's move on then. I think we have a long question coming up. So again, this is one of those, I think, common data questions. So note this down. I'll again come back here. So for this GPU architecture, we have 20 SMs. Max threads per SM is 2048. Max blocks per SM is 32. Registers per SM is 64K. Max shared memory per SM is 128 KB. Now the given kernel performs transpose of a given dataset without any coarsening. Here is the kernel. Tile dimension is 32, block rows is 32. It's called transpose coalesced, and there's a tile of tile dimension cross tile dimension, and your x and y are calculated this way, and you have a for loop that does this. I think I won't read this out. I'll pause here, right? This is the kernel that does transpose. I'll come back here and leave it here. Let's look at the question before that. The launch parameter is a block of this dimension 32, 32, 1, a grid of 64, 64, 1, and you are calling this kernel with this launch parameter. Now the question is, calculate the optimal coarsening factor for thread level coarsening, assuming that you coarsen it only along the x dimension. So your options are 2, 4, 8 and 16. Now I'll go back and please note down these options, and I'll go back to the kernel, right? So here are your block and grid dimensions, and I will stop here, and you can look at this kernel in detail and take 5 minutes to solve this. I think you had a similar example solved in class. And if you want either the options or the previous slide, let me know the GPU architecture details. I can scroll there. But try to solve this. I know it's a lot of information, but think about it stepwise and try to solve it. You want the options part of it or the earlier part about the GPU architecture? Okay, I'm assuming this is fine. If you want something else, let me know. Okay, does anyone need more time to solve this or shall we look at the solution? Okay, if you don't want more time, we can go ahead to the solution. So it is 16, option D. So let's start with, so first of all, we are asked for the optimal coarsening factor for thread level coarsening, and assuming that we coarsen it only along the x dimension. So now, if let's assume, so we are trying to find this x, right, the coarsening factor. So for now it's an unknown, right, we just call that x. So the block size is given to us as 1024, 32 into 32 into 1 without any coarsening, right? Now with coarsening, if you coarsen along the if you coarsen with some factor x, the new block size would be 1024 divided by x, and for that block size, the number of active blocks per SM would be 2048 divided by this new block size. Where does the 2048 come from? It comes from this max active threads on an SM, right? You can have 2048 threads on DSM, and your block size, new block size with the coarsening factor is 1024 divided by x. So the total number of blocks you can have is 2048 divided by this new block size. That comes out to 2x, right? So, and for thread level coarsening, the shared memory requirement per block would remain the same. It doesn't change. So coming to the shared memory requirement per block, how much is it? It is 32 into 4 bytes, right? And that 4 bytes is I think the same that was used in the class example also, right? The shared data that is accessed, that is I think of type float here, and that takes 4 bytes, right? So your per block requirement of shared memory is 4096 bytes. So per SM, how much shared memory do you need? It would be number of blocks per SM into shared memory per block. Shared memory per block we've just calculated. Number of blocks per SM is 2x, right? So shared memory requirement per SM is 2x into 4096 bytes, right? And the max allowed shared memory per SM as per hardware is 128 KB. Now your optimal coarsening factor would be such that this 2x into 4096 is equivalent to 128 into 1024 bytes, right? So then you solve for x and you get your x to be 16, and that comes out to your option D. This is a very long solution, so I'll pause here for 1 minute. And I think we didn't go through thread coarsening today. So if you feel you don't understand thread level coarsening very well, you don't understand some of these things like shared memory requirement per block is the same, you don't understand some of these things, feel free to say that also, right? We can talk about thread level coarsening and block level coarsening in the next class and go through these questions again. I'm fine doing that. The assignments might be over, but it will at least help you for your final exam. Is thread level coarsening clear to everyone? Feel free to say no if you're confused. There's nothing wrong with that. Okay, that's good. So we can do that. I think this is the third type of question, right? So the first type of question was, I think your question 1 and 2, where we are talking about number of cycles for different fusion techniques. The second type of questions was the kernel launch parameters, which is straightforward. And I think we have 3 questions which are very similar to this, which asks about the shared memory requirements or the optimal coarsening factor. So if you don't understand this very well, I think what we can do is spend some time recapping the coarsening factor and the thread and block level coarsening. Then we'll come back to this question and the 3 questions that follow it, and we'll go through them in detail. That way at least you'll be clear with whatever few questions we solve. So I won't solve the other 3 questions today itself. I will do that next time so that you understand it better. I think without a recap, I assume that you know what is thread level coarsening, you know why this is true. That might not be the case, right? Because these are advanced topics, you might be confused about them. So we can spend some more time next week. Sure, we'll do that. So in that case, I don't have any other questions that are unrelated to this. I think the 3 questions that follow this are all on thread level coarsening. So like I said, I'll do that in the next live session so that it will help you. But let's use these last few minutes to see if you have any other questions or doubts so far in the course. From let's say week 1 to week 8 or even week 10, are there things that are difficult, right? Because remember that we have one live session per week. So when your week 12 is done, we'll have one live session covering that week's contents, and there's not going to be a live session that's kind of summarizing everything or having doubts across the course. So use these last 3-4 sessions to ask, spend some time on question 7 and 8 in week 9 assignments. Sure, I don't have any problems. When is the deadline for that, by the way? assignment. Okay, looks like multiple people have a doubt in question 7 and 8. Oh, Wednesday. Okay, I haven't looked at this assignment at all yet. So, okay, let's think about this. So, do you think the options are wrong or something like that? Like, do you have a doubt that needs to be addressed before you can solve this question, or are you just finding it difficult to solve it? See, so if you think the options are wrong or there are multiple correct options or something like that, please ask it on the discussion forum because there's still a couple of days, right? So they might be able to give you some pointers on that, saying maybe the question is wrong or maybe there are multiple options, both will get correct answers. If that is not the case, you're just unable to kind of solve this, then we can definitely take it up in the next week's session. But for me to go through this before Wednesday and maybe put some information in the slides will be difficult because I haven't gone through the videos of this week 9 yet. So I don't have a very good idea of what was covered in the class and then what these questions are. So that will be difficult, but we can definitely solve both of these questions in the next week's live session. I will note them down right away and we'll spend time on that. Sure, you can do that. Yeah. Yeah, I will do this. And okay, week 10 I think was just released, right? So week 10 I think you will have a little more time in terms of deadline after the next live session, but I don't know when it was released and if you guys have already gone through it. So if you tell me a week in advance, I'll be able to definitely solve them and come before the next live session and maybe help you a little. But again, I think week 10 would have probably been released yesterday or today, right? So I don't know if you guys had the time to look at it. I'm assuming you don't have anything in week 10. Next week, maybe in Monday again, like this, you can tell me if there are a couple of questions. I'll try to look at week 10 in advance. Again, I don't know how much material there is. So I also need to find the time to watch these lectures and then go through the assignments. But solve week 10 in advance maybe and see if there are certain questions that you find difficult. Then we can try and at least solve those. Okay, so for today, I think that's all I have. Yeah, I definitely agree. I think that is something you should mention in the feedback, right? Because I have also been watching the week's lecture videos. I think, like I said, till week 5 or week 6, there was a lot lesser in terms of content per week. But from week 7 onwards, I see a lot packed into every week, and that's because I think the lesson plan is made topic wise. For instance, there is kernel fusion and thread coarsening that is packed into 1 week, regardless of how much content that has, right? So, whereas some of the earlier weeks were very light. So, the way the course is structured should be slightly different. So, in the feedback forms that you get, make sure to mention that maybe they will change it later. And it will help other people who are taking this course. I will do the same, but for this time we can't do anything. It is what it is. So we have to try and manage it the best we can. And again, I'll remind you, think about all the weeks, start revising the entire week's contents in the next 3 weeks, right? Ask me doubts from any week from next week onwards, and because we just have 4 more sessions left, right? And you have to ask me the previous week for me to come back with information about it. So we have only 3 more weeks where you can ask questions and then I can come back with some info about it. So start going through things from week 1, all the assignments, live session material, everything, and then if you find some topics that you don't understand, point them out, right? We'll split them up into these 3 weeks and cover them. How was the subjective assignment evaluated? I am not sure. Did you receive the, I think this was the week 4 one, right? Did you receive scores for it or something like that? Or did you receive some kind of feedback? So there might be two ways they could have evaluated it. They might have simply used a script to check if your output kind of matched whatever. Okay, compilation successful, kernel code not correct, launch parameter not correct, syntax error, test failed. Okay, this looks like an automated evaluation, right? So they might have had some script kind of check your code and how it worked with those test cases. Syntax errors and things like that, I'm not sure how they check, but each of these points or these test cases, these steps might have had points, right? Like compilation successful might have fetched you some points, and tests passing might, launch parameters might be another step, and then tests passing might fetch you some more marks and things like that. You also got the marks or the breakup or something like that, is it? What exactly are you looking for? Are you looking for the breakup of marks between these, or do you have more subjective assignments, by the way? I don't think I've seen any so far. If that's the only one, I think at this point that won't help you much. Since I was told, okay, you got the correct output on your machine. Okay, I see. Okay, it says compilation successful, but launch parameter is not correct. You can ask on the discussion forum again to see if have they released a solution for this, and does it match whatever solution you kind of proposed. Yeah, you can ask, since the deadline is over, you can kind of ask and share your code also and ask what are the places where it is wrong. They may or may not have the time to look at it, but no harm in asking, right? You can ask and see how you did. Okay, I think we're almost at the hour, so I don't have anything else for today. So there are no other questions. Thank you so much for joining. Hope this was helpful, and don't worry if it's too complex. I'm sure all of you will do well. Just keep at it, right? Don't give up now. I know a lot of people, when it comes to post midpoint of the course, it gets too difficult and people think, oh, I can't do this. I'm sure you can do it. You've been there for all these weeks, so keep trying to understand it. Ask questions, ask doubts, and try to do your best. That should be fine. So see you guys next week then, and come with doubts and questions. Make the best use of these live sessions. Good to hear that. I understand, right? I'm still a student and I've taken very difficult courses too, so I understand what you guys are going through. I've been on both sides, so don't worry about it. It happens to all of us. Okay, if that's it, thank you and have a good evening. See you next week.